Hello. Today's lab experiment is on meters, and we'll be using an instrument called a galvanometer to measure different quantities, different electrical quantities, starting with current, which is obvious enough, but we're also going to measure voltage and we're going to measure resistance using a simple device called a galvanometer. And so let's talk about how that works. So a galvanometer, basically the dial moves with current. It's a coil of wire wrapped around a dial. When you put current through that wire, it creates a magnetic field. The magnetic field makes the wire, or makes the needle tilt in proportion to the amount of current. And so galvanometers are typically sensitive to small amounts of current, and but we're going to be looking at that through the course of this experiment. So the deflection of 1 on the galvanometer, meaning a full-scale deflection, corresponds roughly to 1 milliampere, but we're going to be getting a more precise reading on that. So you're going to set up a circuit, and the first thing you're going to do is basically see, well, how much current do you need to put in? So you're going to connect the galvanometer to a digital multimeter that's measuring current. So how much current do you need to put in to get the dial to tilt at full scale? And you're going to be using that throughout the rest of the experiment. And then you're going to calculate the voltage across the galvanometer and also the resistance across the galvanometer. And so we've measured those things to see what full-scale deflection is, and also to see what the resistance across the galvanometer. That's a very important measurement because it affects everything else that goes on in the course of the experiment. So this is basically how multimeters work. They work with a simple galvanometer in tandem with a bunch of other things to get the measurements that you see. So we're going to start with an ammeter. So the galvanometer is sensitive to currents of 1 milliamp. Well, what if you want to measure larger currents than that? What do you need to do? So for an ammeter, what you do is you connect the galvanometer in parallel with a shunt resistance. So the galvanometer has its own resistance, and you're going to put that in parallel with a shunt resistance, or that's what we do in the procedure, and you can see how that works. You're going to be asked to calculate what the value of that shunt resistance is. When you see the experiment, it's going to be set up on a variable resistor, but I tried to hide that value. Maybe you'll catch it, maybe you won't, but it's your job to calculate what that value should be. And so you want to turn the galvanometer to an ammeter that reads 5 milliamps on full scale. So you know the full scale current, and you know the resistance of the galvanometer. These are things that you will measure, and you're asked to calculate the shunt resistance from that. So basically you have a parallel segment, you have the galvanometer and its own resistance in parallel with the shunt resistance. So you're going to need to figure out what that shunt resistance is. And so then once you have that, you're going to go through the experiment in steps. So you try to figure out, well, what current gives you is 0.2 times the maximum deflection, what current gives you 0.4 times the maximum deflection, and work your way up to full-scale deflection. And again, if you've done that right, your full-scale deflection should equal 5 milliamps. And it should be a nice proportional relationship, but you'll see how well that works. And if it's not exact, try to explain what could cause differences. Then we move on to using the galvanometer as a voltmeter. So remember, galvanometers technically measure current, but you can measure the voltage across a segment of the current as well. So what you're going to do is set up what's called a voltage divider. So a resistor is connected in series with the galvanometer, to calibrate the galvanometer so that its maximum current responds to the desired voltage. So you're going to figure out what voltage you need. So again, you have this variable resistor that you're going to adjust. And so the resistor is connected in series with the galvanometer. And remember, the voltmeter is connected in parallel with the segment of the circuit that you're measuring the voltage across. So you want to figure out what voltage you need. Again, so there's a little bit of math involved. What is R sub V, the additional resistance that you need in series with the galvanometer, so that the maximum deflection corresponds to the maximum voltage on your setting. The power supply we have doesn't go up to 25 volts, so we couldn't use that. I think I only used 5 volts as the maximum, but you can double check that. But I think I only used 5 volts as the maximum, so you can adjust that. And again, does 0.2 deflection give you 1 volt? Does 0.4 times the maximum deflection give you 2 volts, and so on, like that. So you'll be setting up that table and looking at the measurements. And again, if the measurements, if you don't get a nice linear relationship, try to explain why. That brings us to the ohm meter. The ohm meter is a bit more complicated because unlike the current and the voltage, which are going to be inversely proportional to, or directly proportional to the deflection, the resistance is going to be inversely proportional to the deflection. So it's going to be a little bit more complicated. But an ohm meter has in series a combination of the galvanometer, the resistor, and a resistor that you're going to need to calculate, and a voltage source. So an ohm meter has a built-in voltage source in it. So an infinite resistance gives 0 current. So remember, with an ohm meter, you're disconnecting the resistor from the circuit. So you basically have a circuit with the galvanometer, a resistance R omega that you're going to calculate, the voltage, which you're also going to calculate, and the unknown resistance you want to measure. So an infinite resistance gives 0 current. An external resistance of 0 should give the maximum current. And we want a half deflection. So when the current is halfway deflected to respond to 4 kiloohms. That gives you enough information to solve for the resistance you need to add to the ohm meter in addition to the galvanometer's resistance. So that's R omega and V. So that gives you enough information to make those calculations. So you're going to adjust the resistance, and so in the procedure, we're adjusting the resistance and recording the corresponding deflection. So basically, we've got a variable resistor that we're going to use and adjust that resistance until we get the deflection in certain places. So we're going to look at 0.8, 0.6, 0.5, 0.4, and 0.2 times the maximum deflection, and what resistance gives us those deflections, and compare those with the theoretical results. So once you have R omega and once you have V, you should be able to come up with theoretical results for each of those values. And so you're going to compare them and get percent errors. And then you have 9 questions on page 46, basically the back end of your manual for this experiment, that you're going to answer for the lab report. So if you have any questions, do not hesitate to send me an email and ask for help. Okay, thank you and good luck, and we will talk soon.